It's February 3rd. A freight train carrying hazardous material derails on its way through East Palestine, Ohio. The wreckage catches fire and releases deadly chemicals into the air, forcing an emergency evacuation. Even today, almost a year later, we're still trying to clean up the mess. Now, Norfolk Southern Railway has caught a lot of flack over the incident. Yet, despite being a chemical spill, nobody seems to be talking about the environmental impact of the chemical industry. Hi, my name is Ryan Kwok. I'm a second-year graduate student in the chemistry PhD program here at CUNY, and today I'll be telling you a bit about my thesis project. According to the EPA, chemical manufacturing produces over 500 million pounds of chemical waste. A majority of this waste is what we call solvent, and the topic of my thesis, mechanochemistry, tries to be environmentally friendly by just not using any solvent. Let me explain. So let's say you wanted to run a chemical reaction. You have your starting material, your reagents, but for them to actually react, the reactant molecules need to collide with the proper orientation and energy. The solvent allows these collisions to occur by acting as a mixer for your reagents and the energy we usually get from heating your solvent. This is an oversimplification, but it's basically how chemistry has been done for centuries now. The problem is, you often need a lot more solvent than reagents, and you can't exactly reuse your solvent without purifying it first, and this is what leads to a ton of waste. On the other hand, mechanochemistry uses mechanical force to both mix our reagents and as a source of energy. The result of this is that now we don't need any solvents at all. And this is great, but good luck convincing a company to convert to mechanochemistry just because it's more environmentally friendly. The reality of capitalism is that they'll probably just laugh in your face. Fortunately for you mechanocapitalists out there, mechanochemistry is more than just sustainable. Mechanochemical reactions can be faster than traditional reactions and can even form what we call impossible compounds, which, as the name suggests, are compounds that you cannot form using heat and solvent. What this means is that mechanochemistry has the potential to develop entirely new compounds, which can then be further applied in, say, medicine or material science. And since we're not using solvent to make these compounds, it's all sustainable. But I'm not a mechanocapitalist. I'm a cross-cutting computational chemist. So I'm more interested in why we see these effects. Right now, the working theory is that these differences are the result of force-induced molecular distortions. To explain this, though, I'll need to go over something we call potential energy surfaces. So this is what a generic potential energy surface will look like. Here are our reactants, our products, and what connects them is called the transition state, which is the moment your reactants have the proper orientation and energy. Now, the transition state is really the star of the show here. The relative energy and the structure of the transition state tells us how fast the reaction will occur and which product we'll get. In other words, if you control your transition state, you control your reaction. Traditionally, this is done by changing your solvent. Some solvents stabilize certain transition states over the other, and this will speed up that particular pathway. In mechanochemistry, though, we don't have a solvent to change. Instead of stabilizing the transition state, we're actually going to destabilize both the transition state and the reactant by distorting them. Now, this seems a little counterintuitive, but let's think about the relative barrier here. If my reactant is distorted to look like the transition state I want, the reactants will go up in energy, but the transition state doesn't go up by nearly as much. This lowers the relative barrier, even though now the absolute energy of both the transition state and the reactants are higher. Now, this explains why some reactions can be faster using mechanochemistry. But what if I wanted a different product entirely? Well, in theory, all I need to do is just distort my reactants to look like that product's transition state. Again, it's not entirely that simple, and there's still a number of questions that haven't been answered yet. For instance, we know that force can lead to these distortions, but we're still not quite sure how to distort things a certain way yet. And actually figuring out those answers is what my thesis will be about. Hopefully I'll be able to get back to you on that in a few years, but in the meantime, thanks for watching.